Hey, what's up? This is Mr. Kern. Today we're looking at lesson 16 of the Smells unit, Polar Molecules. Now on this, we're going to have some drawings of some penguins and polar bears, and you don't have to be a spectacular artist. This is what I would put in my notes. They're lovely, if not misshapen. And he lost his face. Okay. The importance for this is we're going to be looking at characteristics of molecules, and for you to understand why the molecules behave the way they do, you need to understand something about what's going on inside of them. We've already looked at the shapes of molecules. Now we're going to look at what else is going on inside those bonds as they're formed. So, do the comic strip. We've got this lovely, if not biologically incorrect, illustration of the penguins and polar bears. If that's a periodic table, this would be the noble gases. Up here you have the non-metals. In this area, pretty much from here on, you have the metals. I would sketch this out, really generally, if I were you, in your notes. And just draw a couple penguins, just say penguins here and polar bears over here, but noble gas has nothing, because they don't react, so we're just going to ignore them. Alright, so basically what goes on is, as these things bond, you're going to get different sizes of these molecules, different strengths. So if we have fluorine, fluorine is the most, I guess, the biggest polar bear, the strongest. So it's going to live all the way up here. So if these guys are bonding, the book had them sharing ice cream cones in the middle. Now, I don't know the whole origin of the ice cream cone, like each of them was walking around with one ice cream scoop, because that's an electron, saying, hey, I need a partner for this, and somebody else is walking around with their scoop saying, hey, I need a partner for this. No, we've got a cone here. I don't know who brought that, but let's just pile these together. So they're both grabbing onto this ice cream cone, sharing it in between them. We could have a different kind of pairing where we have chlorine and bromine. Now that's a bigger polar bear with a smaller polar bear, and that's going to have a little bit of difference in how those guys behave, but still each of them provided an electron. That's what the ice cream cone is, and so they're both sharing. Now the book had a lot of illustrations where one of these guys would overpower the other. So one of the things we'll look at is, how do you know whether or not it's pretty even, like with two F's, because they're going to be the same strength, or if this guy being bigger is going to overpower the little one. We have hydrogen and fluorine. Now hydrogen lives all the way over here. It's a non-metal, so like one thing we'll look at later has it living up here. But it's a non-metal, it lives over with the metals, so it acts like a penguin. It's not going to be as strong. So if these guys partner together, what the book showed was that this guy is going to be hogging the ice cream, but this guy's still holding on to it. He's still grabbing. Now again, I'm assuming in your notes you're drawing these pictures, the lovely sketches of these, and basically making a match. You can write notes. Share equally, share unequally. Does that one fully more? This one, they're still sharing way greater than on that one. And the last one you have, sodium would be right here. That's a smaller penguin. But you'd have sodium and chlorine. Now the difference on this is sodium, I guess, hydrogen is a non-metal and fluorine's a non-metal. Sodium is a metal. So a long time ago, back in the day, we talked about metals and non-metals and how they interact. And so we know that with these, the metal gives away its electrons. So both of the ice cream cones are fully held by the polar bear. And basically there's kind of this electric attraction, because that leaves the metal being positive and the non-metal being negative. So at what point is I guess at what point does the polar bear totally take away the electrons? At what point does one element totally steal the electrons away? Where do we call that this is even or not? And we're going to put in some numbers for that, and we'll kind of play around with them more next class period. But the basic idea, I guess, on the last one is, on that one, the positive and negative interaction holds them together like a magnet. Alright, so really what we're talking about with the strength of the polar bear is electronegativity. On here, we're going to bold and underline this, and italicize it, and make it bigger. Okay, electronegativity, well, no, electronegativity is a big thing. At the end of this, in past years, it's been like, hey, what's electronegativity on a test? It's like, well, I don't know. Like, you have to know electronegativity. It is the really biggest thing for why these things act the way they do, why the elements act the way they do. We can look at it as how greedy they are for electrons, or size of your polar bear. Size has an E. Size of the polar bear is another way to look at it. So we actually have numbers for these. That's the electronegativity. So we said the biggest polar bear is fluorine. Fluorine lives up there, wherever the littlest penguin live. Right there. That's francium. So if we look at francium, sure enough, that's the smallest number, 0.7. So that's its electronegativity value. Now we cut out basically this, cuts out the metal. That would live right here. And because all we really care about are the ones on this end and the ones on the other end. So a big electronegativity means it's very greedy. A little electronegativity number means it's not very greedy. That's your penguin. That's penguin there. Alright, so I guess some thoughts on this, how it ends up working. I do not expect you to write all these words down. It's better if you can put some of this in your own words a little bit. But basic idea is, if one atom is more electronegative than its partner, so you have a polar bear and its partner being a penguin. There's the okay. It wins, so the polar bear wins. Yay! And it hogs all the electrons. Now, sometimes they're still connected with that though. Because electrons are negative, he just got a bunch of electrons. That makes the electronegative end of the molecule, that would be the polar bear, a little bit more negative. So he's a little bit negative. We're going to put negative-ish. And it makes the other end positive-ish. They're not completely positive or negative like with the NaCl earlier. If one end is partially negative, so we call that a partial charge, and the other end is partially positive, that is called a polar molecule. That should be really big with a giant star beside it in your notes. Is a polar molecule. One end of it is positive, one end is negative. So where is the dividing line between these guys are sharing it evenly, this one's hogging it, or they're totally separated because one of them took it away? What that ends up being is basically this little chart here. So arrow, electronegative difference. We're going to be subtracting on here. If the difference is 0 to 0.5, so the strength difference is in that range, then it's one thing. If it's between 0.5 and 2.1, it's something else. If it's above that, it's another thing. So things that fit in there is sorry, I was listed wrong. Alright, so if the difference between the two things, the difference between the two polar bears is from 0 to 0.5, they're both the same strength, that would be called nonpolar. If one of them is a little bit stronger, you're going to have a little bit of difference between their strengths. That's going to be called polar. And if there's a big difference between the two strengths, that's going to be ion. Now with these, those two are both covalent because it's a nonmetal plus a nonmetal. The ionic is a metal plus a nonmetal. So again, we talked about these a while ago. Now we're really learning about why it is that they would act differently. Why do they become positive and negative? Because one of the elements is stronger. So let's look at some examples with this. Let's look at examples we already looked at. If we want to actually calculate up and figure out is each of these things polar, nonpolar, or ionic, we need to take a look at their numbers. If we have fluorine and fluorine, we have a 3.98 and a 3.98. So we're going to figure out the difference between them. So I subtract, the difference is 0. So where does that lie on this? Well, that would be right there. So fluorine and fluorine, that molecule is nonpolar. If I look at chlorine and bromine, that was a big polar bear and a little polar bear. So is their strength going to be different enough to make it so that this guy hogs the electrons, or do they share evenly? So we have to look at their numbers. Chlorine has a 3.16. Bromine has, the R is there, they left off the R, a 2.96. So we hit pause and we calculate that. Alright, according to our calculator, the difference is 0.2. So if the difference is 0.2, I guess we can put these on here. This is FF. So 0.2 would be in here. So that's Cl and Br would live there somewhere. So that would also be nonpolar. That means both of these guys still share the electrons evenly. Alright, now we have H and F. So F is 3.98, H is 2.2. So hit pause, see what that is. Alright, so on mine, I set it up like this, 2.2 minus 3.9, it doesn't matter whether you get a positive or a negative. Sometimes kids get very concerned about the difference on there, but it's 1.78. Yeah, it doesn't matter which one you subtract. It makes sense maybe subtract the little one from the big, but just take the absolute value. So that puts it right here. So that makes hydrogen fluoride in this category. That would make it polar. So we do a special thing when it's polar. We write polar first off, but we draw this thing. The electrons are going to go toward the bigger one. That's the fluorine. So we draw an arrow toward the fluorine. That means the electrons are traveling that direction. On the other end, because the electrons left it a little bit, not totally, just a little bit, we do this. So this is a partial positive end. This is partial negative. So positive end, negative end. And what we call this is a dipole. That is the thing we drew. So a dipole is that arrow right there. And this is the kind of thing you'll be doing on the worksheet next time, is you'll look at molecules, figure out, is there a dipole or not? If there is, you draw the dipole. Alright, for the last one, see if you can find the things and figure out what it is. So, sodium is 0.93, chlorine is 3.16 on the table, there. You subtract them out, you get 2.23. You put that on this little handy-dandy chart, that would live right in there. So Na and Cl, as predicted, because it's metal and non-metal, would be ionic. Ion. The electron goes all the way over here. That makes this one totally negative, not partially, but totally. This one totally positive, and that's why they stick together. So that's the kind of thing you'll be working on next time. We'll do it a little differently, though. Also, if we look at water, an H2, an H, and the 3D-ness of it that we've talked about with our molecule shapes means it looks basically that bent shape like that. So if we're going to bond those, is that polar or not? 3.44 and 2.2. 3.44 minus 2.2. That's going to be a 1.24 difference. That's bigger than 0.5. So that means these are polar. So we draw two dipoles that would look like that. That means this molecule as a whole, if I split it left and right, this side and this side look the same. They have the same charge. They have that partial positive charge. So the molecule as a whole, in that case, has two positive ends. If it has two positive ends, that's not like a magnet. A magnet has the positive end and a negative end. But if I split it top to bottom, if I split this molecule top to bottom, if I lay a ruler on it like that and look at it sideways, this end is positive. This end is negative, partially. And so the molecule as a whole does have an entire big whole molecule dipole. So we would draw it like that. So the whole molecule is polar. And the bonds are also polar. There are examples, though, where you have polar bonds but not polar molecules. So we'll look at those next time. But this is the type of thing we'll be doing next time. If this entire molecule is up here, is the whole thing polar or not, based on the dipoles. So we have that to look at next time. And we get to do a lab, too, where we squirt liquids and we have a magic wand that does stuff. So be fun.